Hello Chem 1A, this is Chapter 3, Lecture Video 6, and we're going to be talking about two kind of different topics in this video, one being organic compounds and a very small bit of naming for them, and then that'll close out naming for the entire class. After that, we're going to talk about the mole, and that's a pretty big deal. So, organic compounds are compounds that contain generally carbon, oxygen, hydrogen, sometimes nitrogen, sulfur, phosphorus. Also common is like the halogens attached to these things. But the primary things that we're going to see in organic compounds are going to be carbon, hydrogen, and oxygen. These are our main kind of three. And honestly, the carbon and hydrogen are way more important. So we're going to talk only about the simplest type of organic compound, which is known as a hydrocarbon. Hydrocarbons only contain carbon and hydrogen and no other elements. And there are actually three different types of hydrocarbons out there. There's alkenes, alkynes, and alkanes. And we're going to talk about the simplest of those hydrocarbon compounds, which is the alkane, which is a organic compound that contains only carbon and hydrogen and only single bonds in the compound. So we're going to learn about the first 10 straight chain alkane names. And I only need you to know the first four. So I'm going to show all 10 just because it shows kind of why they're called straight chain alkanes. But you only need to know the first four compound names that I'm going to list here. So CH4, you should know this guy's name is methane. And I'm going to show you the structural formula of it so that you kind of have an idea about this. You don't need to be able to draw these yet. We'll learn that later in the course. But this is methane's structural formula. It's what it actually looks like. C2H6, you should know that as ethane. And so these two you do need to memorize, both the name and the formula and vice versa. It has two carbons in a row, and you kind of see here we're building a little bit of a carbon chain, and this is why they're called they're called straight chain alkanes. C3H8, another one I do expect you to know the name of, which is propane, common fuel for barbecues. And you can kind of see now we have three carbons in a row here. The last one I expect you to know the name of is C4H10, butane, also a fuel that we use for barbecues, stoves. If you go camping, you usually use a butane stove or butane torches for lighters. It's four carbons in a row. So these are the ones I expect you to memorize. The rest I'm going to show you, but we don't need to know the names or their formulas for them. At least you don't need to have them memorized. We may use them in problems, but in that scenario, I'll give you the formula. So C5H12 is pentane, 5 carbons in a row. C6H14 is hexane, 6 carbons in a row. C7H16 is heptane, 7 carbons in a row. C8H18 is octane, 8 carbons in a row. And C9H20 is nonane, and 9 carbons in a row. And finally, decane is C10H22, and it has 10 carbons in a row. So you can kind of see why these are called straight chain alkanes, because it creates a chain of carbon atoms. All right, so again, can't stress enough, only need to know these first four, right? So butane through methane group here. These are the ones you're responsible for memorizing. I won't give you their formulas. If I use any other organic compounds in the class, I will provide the formula for you. All right, so let's talk about the mole. The mole is not a furry woodland creature, even though they are cute. It's not a skin thing where we have like too much melanin building up in our skin and a cluster of it. That's kind of what a mole is, if you didn't know. It's not those. At least, I mean, when we talk about it in terms of respect to chemistry, we're not talking about those. The mole is a counting unit in chemistry. And what is a counting unit, you might ask? Well, the word a dozen is a counting unit. Dozen hopefully should reflect 12 for you. Now, if I add something to the word dozen, it tells you what I have 12 of. For instance, if I say I have 1 dozen eggs, I have 12 eggs. But that doesn't mean I can't use the word dozen with other things. This is true of the mole as well. For instance, I could have a dozen shoes. That'd be 12 shoes. I could have a dozen elephants. It's a lot of elephants, but we got 12 elephants then, right? Anything I have, if I say the word dozen, tells you that whatever I'm talking about, I have 12 of that thing. That is true of the mole as well. It doesn't always have to be for one substance. It can be for many different things. It's a counting unit. Now, what that means is, like a dozen, if you have a mole, you have a certain number of stuff. In the case of a mole, though, it's a huge number of stuff, right? So if I have 1 mole of, let's say, atoms, then I have 6.022 times 10 to the 23 atoms. Now, that's a big number. You need to memorize this number because I will not be providing it on tests in the class. All right. Now, if I have a mole of shoes, that means I have 6.022 times 10 to the 23 shoes. This is an obscenely large number. Now, because of that, we generally don't use it to talk about shoes. There aren't 6.022 times 10 to 23 shoes on the entire planet. Nobody's made that many shoes, probably, in the history of the Earth, I would guess, because it's so big of a number. So, in chemistry, we typically use it when we're talking about atoms, molecules, ions, protons, neutrons, electrons, subatomic particles, whatever you want. Primarily, we use it with stuff that there is a large amount of present in even small samples, like all of the things I just listed. We also call this number 6.022 times 10 to the 23 by a special name. It's known as Avogadro's number, named after Amadeo Avogadro, a famous chemist from in the past. So I always like to do this because it's really hard to quantify 6.022 times 10 to the 23 in our brains, as we have no reference point for a number that big. I actually looked up what the name for 10 to the 23 is, and it's sextillion. Like, 10 to the 9 is a billion, 10 to the 12 is a trillion, 10 to the 23 is sextillion dollars. So we're going to do a little word problem here to kind of impress upon you guys how big this number actually is. And this is going to be an unrealistic word problem, but it's kind of fun because we get to pretend we're very, very wealthy. So let's say we had a mole of dollars. All right. In other words, we have 6.022 times 10 to the 23 dollars. We are obscenely wealthy people. How big is that? Well, let's say our new family credo is let's go bankrupt. So we're going to see how long it'll take us to spend this money. Now, if we want to spend this money, we got to figure out, okay, well, how much are we going to spend and over what amount of time, right? So we're going to go with the small amount of money of we're going to spend $1 billion an hour. Every hour for every day for pretty much the end of time. All right, so from now on, I'm always going to be spending $1 billion every hour until I run out of money. All right. So just to kind of make life easier for us, we're going to assume that 1 year is exactly 365 days. In other words, we're going to ignore leap years. So let's just assume that. The fact that I'm already talking about years should tell you how long it's going to take us to finish spending this money. In addition, we're going to say, just to make this a little bit more realistic, we're just going to hire like a bajillion financial accountants that just their one goal is to spend our money every second of every day. I don't know about you. I would probably run out of things to buy after maybe 3 hours. But maybe I could go 4. I don't know. But we're just going to constantly buy things. We're also going to put all our money in a giant Scrooge McDuck vault. And if you don't get that reference, watch some DuckTales. Because we don't want to deal with interest because we'd never run out of money. All right, so how long would this take, right? So if we're spending 1 times 10 to the 9 dollars every hour, right? That's our ratio here. We have initially 6.022 times 10 to the 23 dollars. So if I want to run out of money, let's see how long this will take us, right? So 1 times 10 to the 9 dollars down here, dollars cancel, and that's for every hour. Now hours will give us an exceedingly large number. We won't be able to understand how long that is, so let's convert to 24 hours in 1 day and 365 days in 1 year. Okay, if we do this out and calculate this, we get that this would take about roughly 68.7 times 10 to the 9 years. Or, in other words, it would take roughly 68.7 billion years to run out of money. So this would basically have to be a family credo, because we'd all be dead before we even put a dent in that money. This gives you hopefully a perspective of how huge this number actually is. Just so you guys have an idea, the universe is roughly 14 billion years old right now, so we got a while to go before we'd even run out of that money. Also, we'd probably crash the world economy real quick if we spent $1 billion an hour for that many years. The dollar would basically be worth nothing. So anyways, let's move on. So just to give you kind of an idea, the real definition of a mole is defined as the amount of substance that contains as many particles as there are in 12 grams of carbon-12. In other words, in 12 grams of carbon-12, there are 6.022 times 10 to the 23 atoms. In this one beaker, just to kind of give you even more of a perspective of how small atoms are, in 518 grams of lead, this is a 150 ml beaker. You can kind of see how big it is based on the hand holding it. That's 2.5 moles of lead atoms. That means that's 2.5 times 6.022 times 10 to the 23 atoms present in that one beaker. That's huge. And it's not even that much substance. Here are some 1 mole amounts, just to kind of give you an idea of different substances have different weights, and therefore to get to 1 mole or 6.022 times 10 to the 23 atoms, it would have different masses. And so here's a mole of sulfur, magnesium, tin, silicon, and copper. All right, so we're going to use the mole and talk more about conversions with it in the next lecture video. If you have any questions, as always, please don't hesitate to contact me.